Hello, welcome to another Anatomy and Physiology 2 Bio 265 video in a nutshell.
Today we're going to be talking about acid-base balance. The foundation of acid-base balance in the body is this equation. CO2 plus H2O equals H2CO3, which equals HCO3 plus H+. Note that each part of this equation has an equal number of hydrogens, carbons, and oxygens. They're just combined in different ways. Now, carbon dioxide is relatively stable, as is water. They don't blend well or like to combine under usual circumstances. They naturally separate. Consider a bottle of soda pop left out on the cupboard with the lid off and it goes flat. So in order to combine these two molecules, an enzyme is required. That enzyme is carbonic anhydrase, abbreviated Ca. Once carbonic anhydrase combines CO2 and water, H2CO3, or carbonic acid, is created. Carbonic acid is relatively unstable and wants to break apart. When it breaks, it can break apart into HCO3, or bicarb, and a hydrogen ion. A hydrogen ion is acid. Bicarb is a base, the opposite of a hydrogen ion, because it can accept the positive hydrogen acid, removing it from circulation and neutralizing that positive charge. Bicarb and hydrogen are naturally attracted to each other because of their opposite charges. And when they combine, they create carbonic acid again, the guy in the middle. The carbonic acid is unstable and will break apart into CO2 and water again. This process of the things on one side combining into the compound in the middle that breaks apart, creating the substance on the other side, is called an equilibrium reaction. This process goes back and forth across the equation, depending on which ingredients are currently present. Before continuing, there's one simple connection that needs to be made. If you greatly simplify this equation, you reach CO2 equals H+. Remember, H+ is acid. So if CO2 equals H+, the more CO2, the more H+, or the more acid. In that sense, CO2 is acid. Suppose I add carbon dioxide to this equation. CO2 is now very likely to combine with H2O, creating carbonic acid and moving across the equation to create on the other side bicarb and hydrogen. This is an example of a right shift. You can think of this kind of like dumping a pitcher of water on one side and watching the water run over to the other side. Now, if I want to watch a left shift occur, I would need to add either hydrogen or bicarb. Dumping the pitcher on the right side will allow the equation to flow to the left. What would happen if instead of adding CO2, I removed it? Instead of pouring water on, I suck away all the water on one side. Removing things from the equation creates a hole that the water on the other side will rush in to fill. For example, removing CO2 will create a hole, and bicarb will need to combine with hydrogen and rush over, a left shift, to fill the hole. So how does all this relate to acid and base balance? Remember, bicarb is basic, H+ is acidic, and CO2 equals H+. So simplified, we have one thing that's basic and two things that are acidic. If I add acidic things, I become more acidic. If I add basic things, I become more basic. And if I remove one of the two, then the other becomes more dominant. So if I remove CO2 and acid, then I must become more basic. The last piece of acid-base balance is that the left side of the equation is controlled by the lungs, the respiratory system, and the right side is controlled by the kidneys, called the metabolic side. For example, if an individual breathes quickly, they breathe off more CO2 and acid, leaving a hole on the left that the metabolic side will need to rush in and fill, a left shift. And because during hyperventilation, CO2 is lost, the acid we just talked about, hyperventilation makes an individual more basic. In the scenario just given, hyperventilation makes an individual more basic, and it's caused by the respiratory side. So this is called respiratory alkalosis. Now, what would happen if the kidneys began to reabsorb bicarb and add it into the bloodstream? So I will have added on the right side, the metabolic side, meaning the equation will flow to the left, a left shift, and it was a base that was added, bicarb. So the individual is going to become more basic. This is called metabolic alkalosis. Note that in the first scenario, I removed CO2, an acid, making me basic. And in the second, I added bicarb, a base, making me more basic. Now let's apply this to the acid-base questions you might see in real life or on a test. In order to discover whether something is being added to the equation, we've got to have some baseline numbers. So the normal pH in the body, 7.40. The normal amount of CO2 is 40, and the normal amount of bicarb is 24. Suppose that a patient in the hospital presented with the following numbers. pH, 7.46. CO2, 35. Bicarb, 21. The first thing to do is to determine whether this patient is acidic or basic. Everything above 7.4, which was our baseline, is going to be more basic, and everything below that 7.4 is going to be more acidic. So comparing 7.46, we see that this individual is higher or more basic. The question then is, which of the other numbers is causing the problem and which one is trying to fix it? CO2. CO2 is low. Will low CO2 make someone acidic or basic? Remember, CO2 equals H+, or CO2 is treated like an acid. So if CO2 is low, or the acid is low, then that means the base must be winning. So low CO2 would make someone basic. Does that match the pH we're seeing here? Yes, the person is basic, and low CO2 would make someone basic. These two match. Now what about the bicarb? It's also low. Would low bicarb, a base, make someone basic or acidic? Well, a low base will mean that you have to become more acidic. So the low bicarb is doing the opposite. It's trying to fix the problem, the 7.46 basic blood that the patient has. In other words, CO2 is causing the problem, making the individual basic, and the bicarb is trying to fix it by making the individual more acidic. This is an example of what's called respiratory alkalosis. Remember, CO2 is on the respiratory side of the equation, and metabolic acidosis, bicarb's on the metabolic side, is trying to compensate for the alkalytic problem. So respiratory alkalosis with metabolic acidosis trying to compensate. So another example of question. pH 7.34, CO2 47, bicarb 27. Do the same steps. Start at the top. Is this individual basic or acidic? Well, compared to 7.40, 7.34 is low or more acidic. Now our CO2, it's high. It's higher than 40. So would high CO2 make someone acidic or basic? High CO2 is going to make someone more acidic. And the person is acidic, so these two match. Now bicarb. Bicarb is high. Does high bicarb make someone acidic or basic? Well, high bicarb makes someone basic. So this is the opposite of the problem, so it must be trying to fix the problem. So this would be called respiratory acidosis with metabolic alkalosis attempting to compensate. Really pretty straightforward. Thank you, and good luck with your studies.